Hi everybody, welcome to this video on the mean value theorem for definite integrals. In this video, we're going to explain and prove the mean value theorem for definite integrals. We're going to discuss the intermediate value property, and we'll introduce and prove a new rule for definite integrals, the Max-Min Inequality Rule. We'll then use this rule to prove the mean value theorem for definite integrals. The mean value theorem for definite integrals is valid for continuous functions on closed intervals. These terms continuous function and closed interval will be used repeatedly in this video, so we'll provide a description of them now. A continuous function can be described intuitively as a function which we could draw on a page with our pen as an unbroken line without ever lifting our pen from the page, so with no skips or jumps or steps. Also, that being a function which does not increase to infinity or decrease to negative infinity, and it being a function which does not oscillate in an ever-increasing way, because these would be examples of discontinuities. A closed interval from A to B refers to all of the points between the point A and the point B, including the point A and the point B. The mean value theorem for definite integrals states that a function assumes its average value over the interval at least once in the interval. So for a continuous function on a closed interval, there's at least one point on that closed interval where the function is equal to the average value of the function over that entire closed interval. We say this more formally and with a maths equation at the bottom of the screen. If a function f is continuous on a closed interval from a to b, then at some point x is equal to c on the closed interval from a to b, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. What we're going to do now is explain this equation further at the bottom of the screen. This term f of c, that's the value of our function f of x for a particular x value, x is equal to c, where x is equal to c is on that closed interval from a to b. These terms on the right hand side of the equal sign, these describe the average value of our function f of x over the closed interval from a to b. So if you're unfamiliar with the terms after the fraction 1 over b minus a, that is a definite integral, this integral from a to b of f of x dx. We've learned in previous videos that we can evaluate a definite integral of a function f of x by first finding its antiderivative, which we write as capital F of x. Once we found an antiderivative of our function f of x, we can then evaluate that integral from a to b of f of x dx as being equal to capital F of b minus capital F of a. If you'd like to learn more about definite integrals and about calculating the average value of a function over a closed interval, I do have videos addressing those topics, and you can click on them at the top of the screen. For this video, we will be focusing on explaining and proving the mean value theorem for definite integrals. To help us explain and prove that theorem, we now introduce the intermediate value property. A function that's continuous on an interval has the intermediate value property on that interval. A function with the intermediate value property assumes all the values between any two particular values. To help us to explain this, we're going to use an example. If we have a look at the plot on the right hand side of the screen, here we have a plot of y equals f of x, where f of x is equal to x squared. Our function f of x, it's a continuous function that's been defined and plotted on the closed interval from 0 to 2. So from x is equal to 0 to x is equal to 2. If we have a look at our plot there, we can see that where x is equal to 0, our y value, f of 0, that's equal to 0 squared, which is equal to 0. And at the point where x is equal to 2, our y value, f of 2, that's going to be equal to 2 squared, which is equal to 4. Our function f of x, it's a continuous function, and it has the intermediate value property. So our function assumes all the values between 0 and 4 on this interval. So for this continuous function on this closed interval from 0 to 2, our function is equal to all the values between 0 and 4 over this closed interval. If we now think about the average value of our function, we would expect that the average value of f of x equals x squared on the closed interval from 0 to 2, that would be in the range between f of x equals 0 and f of x is equal to 4. For example, if we look at our plot of our function on the right hand side of the screen, here we can see that our values of f of x on our closed interval from 0 to 2, our values of f of x are ranging between 0 and 4. So if we were to calculate the average of those values, we would not expect that average to be greater than the maximum function value of 4, and we wouldn't expect it to be less than the minimum function value of 0. We can calculate what that average value of that function is on that closed interval using this equation highlighted in the red rectangle. The mean of our function f is equal to 1 over b minus a times the integral from a to b of f of x dx. We know that for our example here, f of x is equal to x squared, and we have a closed interval from 0 to 2, so a is equal to 0 and b is equal to 2. So when we substitute these values in to our equation, we get that the mean of our function f is equal to 1 over 2 minus 0 times the integral from 0 to 2 of x squared dx. In our next line, we evaluate this further. Now we have a half times our integral, which we're starting to evaluate in integral evaluation notation. The first thing that we do is that we find an antiderivative of x squared. To find an antiderivative of x squared, we use our power rule. We add 1 to the power, giving us x cubed, and then we divide by the new power, giving us x cubed over 3. So we have our antiderivative x cubed over 3. And then we're evaluating that from 0 to 2. So that'll be equal to capital F of b minus capital F of a, where capital F of x is equal to x cubed over 3. So that all works out to be equal to a half times 2 cubed over 3 minus 0 cubed over 3. And that works out that the mean of our function f is equal to 1/2 times 2.667, or 2 2/3, and that's equal to 1.333, or 1 1/3. So we've calculated that the mean value of our function f of x equals x squared on the closed interval from 0 to 2 is equal to 1.333, to 3 decimal places. If we look at our plot on the right hand side of the screen, we can see that on this plot that there is a point on the closed interval from 0 to 2 where our function is equal to the average value of the function over that entire closed interval. There is a point where the function is equal to 1 1/3. So in this specific example, this particular example is meeting the mean value theorem for definite integrals. It is satisfying that. So, having thought about the intermediate value property and having worked through our previous example, we can see that what the mean value theorem for definite integrals is saying, it does appear to be reasonable. It is saying that for a continuous function on a closed interval from a to b, the function assumes its average value over the interval at least once in the interval. If a function f is continuous on a closed interval from a to b, then at some point x is equal to c in the closed interval from a to b, f of c will be equal to 1 over b minus a times the integral from a to b of f of x dx. What we're going to do now is we're now going to introduce and prove a new rule. That rule being the Max-Min Inequality Rule for definite integrals. And we will use this rule to prove the mean value theorem for definite integrals. So here we have the Max-Min Inequality Rule for definite integrals. If max f and min f are the maximum and minimum values of a function f on a closed interval from a to b, then min f times b minus a, where b minus a is the length of the closed interval from a to b, that's less than or equal to the integral from a to b of f of x dx. And that's less than or equal to max f times b minus a. What we're going to do now is we're going to explain this inequality further. So here highlighted in this red rectangle, this part of the rule says that the integral from a to b of f of x dx is never smaller than the minimum value of our function f times the length of the interval. Now, this part of the rule, highlighted in the red rectangle, says that the integral from a to b of f of x dx is never larger than the maximum value of our function f times the length of the interval. To gain more understanding of the rule, we apply it to our previous example. Our previous example of y equals f of x, where f of x was equal to x squared, and that was our continuous function defined and plotted on a closed interval from 0 to 2. So for that previous example, the minimum of our function, min f on the closed interval from 0 to 2, that's equal to 0. So min f times b minus a, we have that the minimum of our function is 0, and our closed interval from 0 to 2 means that a is equal to 0, b is equal to 2. So min f times b minus a is equal to 0 times 2 minus 0, which is equal to 0. So the part of the inequality highlighted the red rectangle for this particular example is equal to 0. Now for this part of the inequality, for this particular example, we're dealing with a non-negative function, a positive function. So the definite integral from a to b of f of x dx, that represents the area under the curve, which shown here on the right hand side, we've highlighted, shaded in green. Now we can calculate what the area under that curve is by evaluating the definite integral. And in our previous example, we'd evaluated that definite integral, the integral from 0 to 2 of x squared dx. Previously, we'd found an antiderivative, which we'd found to be x cubed over 3. And we'd evaluated it from 0 to 2. So we'd worked out our capital F of b minus capital F of a, which was 2 cubed divided by 3 minus 0 cubed over 3, which worked out to be 2.667, or 2 2/3. So for this particular example, this part of the inequality is working out to be 2.667. Now for the last part of the inequality, for our particular example, the maximum of our function f of x equals x squared, so the maximum, max f, on that closed interval from 0 to 2, for this example, that's equal to 4. So we can work out max f times b minus a as 4 times 2 minus 0, which is 4 times 2, which is equal to 8. Again, for this example, we're working with a non-negative function, a positive function. So this max f times b minus a value, this value is giving us the area of the shaded rectangle, shown here on the right hand side, shaded in green. With this rectangle, its height is equal to the maximum of our function, 4, and its width is equal to the length of our interval, 2. So the area of our shaded rectangle here is equal to 8, and max f times b minus a, that's equal to 8. So when we apply our Max-Min Inequality Rule to our previous example, our previous function on that closed interval, we get that min f times b minus a is 0. It is less than or equal to, so 0 is less than or equal to our definite integral, which is 2.667. So 0 is less than or equal to 2.667, and that's less than or equal to 8. So applying the Max-Min Inequality Rule to our previous example, we are getting results which do appear reasonable. And by working through it in this manner, hopefully this is increasing our understanding of this rule a little bit. So that's our Max-Min Inequality Rule for definite integrals. If max f and min f are the maximum and minimum values of a function f on a closed interval from a to b, then min f times b minus a is less than or equal to the integral from a to b of f of x dx, and that's less than or equal to a max f times b minus a. What we're going to do now is we're going to prove this rule. We're going to prove it with a method using Riemann sums. If you're already familiar with Riemann sums, feel free to skip ahead 1 or 2 minutes, or you can use the timestamps in the video description to do that. Now we'll have a quick recap of Riemann sums. So in previous videos, we've learned how we can construct a Riemann sum of a function. If we look at the right hand side of the screen, here we have the plot of a function y equals f of x. This is a continuous function that's been plotted on a closed interval from a to b. To construct a Riemann sum of this function, we divide the interval from a to b into sub-intervals. Here, our first subinterval from x0 to x1, our second subinterval from x1 to x2, our third subinterval from x2 to x3, and so on, until here in this example, our last subinterval is from x15 to xn. The next thing we do is we select an x-axis value, ck, from each subinterval, and then we multiply each subinterval length, delta xk, by the y value, f of ck, from that subinterval. And then we sum the results for all the subintervals. So to explain that in more depth, if we have a look at the plot on the right hand side of the screen, and if we have a look at that very first subinterval there, the subinterval from x0 to x1, what we do is we select an x-axis value from that first subinterval between x0 and x1, and we call that x value c1. And then we calculate the corresponding y value for that x value, which is f of c1. And we've plotted the point c1, f of c1, on the plot here as that first red dot. We also calculate the length of the first subinterval, which we call delta x1. The next thing we do is we multiply delta x1 by f of c1. So we get the product of delta x1 times f of c1. Then we do something similar for the second subinterval. So our second subinterval is from x1 to x2. And we select one x-axis value from that subinterval from x1 to x2. We've called that x-axis value c2. Then we've calculated the corresponding y value for that x value, which we've called f of c2. We've calculated the length of the second subinterval length, which we've called delta x2. And then we've multiplied delta x2 by f of c2. So we've calculated the product, delta x2 by f of c2. And we've done this for each subinterval, all the way up to our last subinterval. So at our last subinterval, we've done the same. And for each subinterval length, we've done the same. So what we do then is we sum all of those products. We sum delta x1 times f of c1 plus delta x2 times f of c2 plus delta x3 times f of c3, and so on, all the way up to delta xn times f of cn. So the sum of these products, that sum is our Riemann sum of the function. And we can describe that Riemann sum with this maths equation at the bottom of the screen. This is saying that our sum, s subscript n, is equal to, if you haven't seen this notation before, this is sigma notation. So that Greek capital letter sigma, that's describing the sum from k equals 1 to n of f of ck times delta xk. So that says in mathematics what I've just described to you with words. If you'd like to learn more about Riemann sums, I do have a video, Riemann sums and definite integrals, which describes this topic in more depth. For now though, for this video, I will be focusing on the explanation and proof of the mean value theorem for definite integrals. So what we're going to talk about now is the proof of the Max-Min Inequality Rule. Here we have our Max-Min Inequality Rule at the top of the screen. The proof is based around showing that the inequality above is true for all Riemann sums of the function. And no matter how we divide up our interval or where we choose our ck points inside the sub-intervals. And by doing that, that will allow us to then prove that the Max-Min Inequality Rule is true. So to do this, we start with the following inequality. Min f times b minus a is less than or equal to, this is a Riemann sum, the sum from k equals 1 to n of f of ck times delta xk. And that's less than or equal to max f times b minus a. So this is what we're starting with. If we look at our b minus a, highlighted here in this red rectangle, b minus a is the length of the closed interval from a to b. We can partition the closed interval from a to b into a number of subintervals, with delta x, k, being the length of the kth subinterval. So delta x1 is the length of the first subinterval, delta x2 is the length of the second subinterval, and so on. We can express the length of the closed interval from a to b as the sum of each subinterval length. So we can express b minus a as being equal to the sum from k equals 1 to k equals n of delta x k. As we will see by doing this, this would be quite useful to us later on. So for our first part of our inequality, we have min f times b minus a, and we also have that b minus a can be written as being equal to the sum from k equals 1 to n of delta xk. So we can express min f times b minus a as being equal to min f times the sum from k equals 1 to n of delta xk. Now, rather than summing all the subinterval lengths and then multiplying by min f, what we can also do is multiply each subinterval length by min f and then sum all of those products together. And that's what we do. We express min f times b minus a as being equal to the sum from k equals 1 to n of min f times delta x k. And what we do is we replace min f times b minus a with these terms here. And that's what we've now done in the inequality at the top of the screen. Next, we have a look at the right-hand side of the inequality, highlighted in the red rectangle here. So again, we have that b minus a is equal to the sum from k equals 1 to n of delta x k. So we can express max f times b minus a as being equal to max f times the sum from k equals 1 to n of delta x k. Again, rather than summing all of the subinterval lengths and then multiplying that by max f, what we can instead do is multiply each subinterval length by max f and then sum the results. So we can express max f times b minus a as being equal to the sum from k equals 1 to n of max f times delta xk. And we replace max f times b minus a in the inequality rule above with this sum in sigma notation in the red highlighted rectangle. So now we've changed our inequality at the top of the screen here. And when we look at this inequality after we've made these changes, we can see that there's only one term that's changing from one side of the inequality signs to the other. And that is that min f is less than or equal to f of ck, and f of ck is less than or equal to max f. And from what we know about Riemann sums, this will always be true for all Riemann sums, no matter how we divide up our closed interval into subintervals, and no matter where we choose our ck values. Because an f of ck value will always be some function value from a subinterval on that closed interval from a to b. And that's never going to be less than the minimum value of the function over that entire closed interval. And similarly, an f of ck value, that's some function value from a subinterval, that's never going to be greater than the maximum function value over the entire closed interval from a to b. So the above inequality is true for all Riemann sums, no matter how we partition our interval from a to b, or where we choose our ck numbers from the subintervals. Because it's true for all Riemann sums of the function, it'll also be true for the limit of those Riemann sums as the subinterval length approaches 0. And the limit of a Riemann sum as the subinterval length approaches 0, that is the definite integral. So written here in mathematics, the limit as the norm of the partition approaches 0, the limit as the length of the largest subinterval approaches 0, of the sum from k equals 1 to n of f of ck times delta xk, that's equal to a definite integral, the integral from a to b of f of x dx. So what we can do is we can replace our Riemann sum with a definite integral in our inequality here. And what we can do next is we can return the left-hand side of the inequality to what it was originally. Rather than the sum from k equals 1 to n of min f times delta xk, we can bring min f back outside that sum, giving us min f times the sum from k equals 1 to n of delta xk, and we can replace that sum with just b minus a, giving us min f times b minus a on the left-hand side of the inequality, highlighted in red there. And on the right-hand side, rather than the sum of max f times delta xk, we can bring max f back outside of that sum, giving us max f times the sum from k equals 1 to n of delta xk. We can replace the sum of those subinterval lengths as b minus a, giving us max f times b minus a. So we can replace the right-hand side of our inequality with max f times b minus a. And this concludes our proof of the Max-Min Inequality Rule for definite integrals. We're now going to use this rule to prove the mean value theorem for definite integrals. So this is what we're going to prove. The mean value theorem for definite integrals. If a function f is continuous on a closed interval from a to b, then at some point x is equal to c in the closed interval from a to b, f of c will be equal to 1 over b minus a times the integral from a to b of f of x dx. In other words, for a continuous function on a closed interval from a to b, the function assumes its average value on the interval at least once in the interval. So here we have our proof of the mean value theorem for definite integrals. We start with the Max-Min Inequality Rule for definite integrals. Min f times b minus a is less than or equal to the integral from a to b of f of x dx, and that is less than or equal to max f times b minus a. If we divide both sides of the inequality by b minus a, we get min f is less than or equal to 1 over b minus a times the integral from a to b of f of x dx, and that's less than or equal to max f. Now 1 over b minus a times the integral from a to b of f of x dx, that is the average value of the function on the closed interval from a to b. So the inequality is stating that the minimum of our function f on the closed interval from a to b, it'll always be less than or equal to the average value of the function f on a closed interval from a to b. And it's also stating that the average value of our function f on the closed interval from a to b, it'll always be less than or equal to the maximum of f on that closed interval from a to b. So because our function f is a continuous function, it has the intermediate value property. This means that it must assume every value between min f and max f on the closed interval from a to b. Therefore, it must assume the average value of the function f at some point x is equal to c in the interval, the closed interval from a to b. And this concludes our proof. So here's what we've just proved, that for a continuous function on a closed interval from a to b, the function assumes its average value on the interval at least once on the interval. Or more formally, if a function f is continuous on a closed interval from a to b, then at some point x is equal to c in that closed interval from a to b, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. So to summarize, in this video we've explained the mean value theorem for definite integrals. We've introduced and proven a new rule for definite integrals, the Max-Min Inequality Rule. We've used this rule to prove the mean value theorem for definite integrals. In our future videos, we're going to use the mean value theorem for definite integrals to prove part of the fundamental theorem of calculus. I hope that you found this video useful. Thank you for your time and for watching this video. If you have found it useful, please subscribe to this video. Please subscribe to this channel for more content. Thank you for your time and see you next video.